I hope we're good. I think we're good. The awkward beginning of these is always awesome. Maybe. Blinky light. All right, hopefully we're good, or you just listen to me mumble to myself. So I'm going to do this. Welcome to Wakefield Academy. It's like Khan Academy, but I don't get paid for it. So we're going to pick up on alcohol dehydrations. The late class didn't quite get as far as the early class. So we're going to just pick up with alcohol dehydrations and eliminations and then run into oxidations and see how far we get. All right. So I will be living down in the bottom corner. You will have sweet, sweet slides that you can look at. So if you have an alcohol, you can turn the alcohol into a double bond through a dehydration. So basically by removing water. So if you have an alcohol and you treat it with a strong acid like sulfuric acid and you heat it, you will turn that into a double bond. Similarly, if you have phosphoric acid, you can do the same thing and make a double bond. Your products are going to be dictated by Zaitsev's rule. So that means that you're always going to make the most substituted double bond. So you're going to make the most substituted double bond. That is Zaitsev's rule. So for secondary and tertiary alcohols, these reactions are going to go through an E1 type mechanism. So have our alcohol, we treat it with H2SO4. I will make it a little bit different. Whoop. There you go. All right, you will end up with the most substituted double bond. Now the mechanism for this, right, so we're going to draw out H2SO4, well most of it, right, so we need the H and the SO4H. Right, your lone pairs on your oxygen are going to attack the proton of the sulfuric acid. You're going to push the electrons over onto the SO4. Right. So that's going to give you your protonated alcohol. My handwriting's bad-ish, but it's like extra bad with my like magical computer whiteboard here. Right, and you end up making OSO3H minus. So the negative charge that you get when you push these electrons over goes onto the oxygen that hydrogen was on. So you get here, you have water hanging off of your molecule, right? And then that water will just leave before anything else happens. It's going to make a tertiary carbocation. These electrons will just go up onto your oxygen, breaking your carbon-oxygen bond. And you'll generate, in this case, a tertiary carbocation. Now, at this point, you will have something act as a base. Typically, it can be the water molecule you just made, another molecule of your starting alcohol, right? But you need something to come by. We'll use the alcohol in this case. You need something that can come by and now remove this hydrogen, have those electrons come down, and that will lead to your product. Plus, you will also make, make sure it's the right alcohol. Sorry, guys and girls. Right, so These guys are separate. There you go. And you will make another molecule of your protonated alcohol. So this way, you can remove your proton and you can remove this proton and make your next protonated alcohol to carry on this reaction. Now, since it goes through a carbocation, you have to be mindful of possible rearrangements. Right? So if you've got, try the right thing here. Right, everyone's favorite thing, little 3-membered ring here. Right, if you treat this with sulfuric acid and you heat it, right, the product you're going to end up with is that. Now, of course, this is because, right, you make your protonated alcohol. That alcohol leaves as water. Now I have a carbocation beside a small ring. That ring can expand. Right, so if we do our counting, right, 1, 2, 3, 4, 5. So coming over here, we have 1, 2, 3, 4, 5. Right, and so the positive charge that was on carbon 5 ends up on carbon 1. And then from this point, the hydrogen that's on carbon 5 gets eliminated to give you the product. Right, so all of these reactions, you have to be mindful, since they go through a carbocation, of rearrangement. You can use sulfuric acid and or phosphoric acid. We can pick phosphoric acid. Right. You can use this for the elimination of primary alcohols. Right, and get this as your product. The mechanism here is a little bit different because you can't go through an E1 type mechanism, right? You can't make a primary carbocation. So here this goes through more of an E2 type mechanism, but the first step is essentially the same, right? You have, in this case, HOPO3H2. I'll draw that a little bit better. Have your lone pairs on your oxygen. Pull off your hydrogen, kick electrons up onto oxygen. And you get to the same place you got with the secondary or tertiary. Right? You get this positively charged oxygen. You again get to water being on your molecule. Now at this point, as opposed to the oxygen leaving, the water leaving, now you'll have another molecule of alcohol come in and do an E2 type elimination to get you the product. And again, you're going to make out of here your protonated alcohol that you can go through and do your next elimination with. Oops. this. Now let's say you really, really wanted for some reason to make so we'll go back to our example that we did before. So you really wanted to make this for whatever reason. Right, so we had we saw that if you use sulfuric acid or phosphoric acid, you'll make a carbocation and it won't work. Right, but what you can do is you can use phosphorus oxychloride and pyridine to do this elimination. So this does not go through a carbocation, so you don't have to worry about any additional reactions. It doesn't react with other functional groups. So sulfuric acid and phosphoric acid are very strong acids, and if you mix them with a complicated molecule, they're going to find other things to react with than just your molecule, right? But phosphorus oxychloride is selective for just reacting with alcohols. So we could use POCl3 and pyridine. Oh, I'm sorry. Crap, Mike. I'm sick. My bad. My bad. Right, if you had this double bond, and maybe an ether, and you try to do an elimination with this with sulfuric acid, you might react with the double bond in some way, you may react with the ether, right? It would just be a mess. But with phosphorus oxychloride, you will simply just react with the alcohol and make a double bond. Right, so if you remember when we talked about eliminations last semester, right, where our leaving group is, well in this case our hydrogen, our alcohol, is our alpha carbon. And then the carbon that you're going to make the double bond to is your beta carbon. So you're going to always have your double bond between your alpha and your beta carbon. So in this case, there's only one way to go. Oops, might help if I actually drew the product. Oh no, I was right it right. Right, so you're going to put in your double bond, but you're not going to react with anything else in the molecule. Right, mechanistically, mechanism here. See POCl3. Oh, no, I'm sorry. I totally not the same reagent. Did I mess it up on the last slide? Nope. Momentary old man moment. POCl3. All right. So the product is going to be this alcohol, oh sorry, this double bond. So the mechanism here, it's just like the mechanisms we saw for bromination with phosphorus oxychloride or chlorination with thionyl chloride, right? So first step, what does phosphorus oxychloride look like? It looks a lot like phosphorus tribromide, except for it has this additional oxygen group on it. This oxygen group right here makes the phosphorus very electron poor. So it's very easy for the lone pair on your oxygen to add to that phosphorus, and it will displace your chloride. right? And we get that structure there. So just like we saw before, we now have a positively charged oxygen. Oop, that was bad. Right, now we have a positively charged oxygen. Now our pyridine that we have in that reaction, just like we saw with the other the other reactions, that pyridine can act as a base and remove this proton. And we get to this right here. Now this is a very good leaving group. So I should make that a letter. There we go. So that is a good leaving group. Now at this point, pyridine or another base did we, oh no. Oop. I lost the carbon. Oh no. Oh no. I'm sorry. I'm going to blame it on being sick. How about that? Is that a reasonable excuse? We'll go with that. No one's here to argue with me, so I'm totally sick. I can't do this. I'm all hopped up on Sudafed and ibuprofen. Whoop. There we go. That's better. Mea culpa. My bad. Now you're going to have this hydrogen, a base, another molecule of pyridine, or some other base that may be in the solution. I'm just going to use pyridine in this case. Like this. I'll redraw that. You're going to grab that hydrogen. These electrons are going to come down. And you're going to push out your leaving group. And that is going to make your product. Right, if I draw it like I had it on the first slide, just so there's less confusion, if I can remember it. Oh my gosh, what is wrong with me? Right, these two things are the same. So you make a good leaving group, and then you are able to displace it rather easily. Sorry, I kind of zoned out there. I was looking at my notes. Figured you needed a break. Let's actually put that oxygen on something. That might be awesome. It's a little bit better, I guess. All right. It's weird. Like, usually when I'm quiet in class, like, people are talking behind me or yelling at me. In the empty room, it's just silence. Cold, unfeeling silence. All right, so if we look at this, our phosphorus oxychloride is going to do an elimination. It's going to follow Zaitsev's rule, so you're going to end up with the most substituted double bond. If you have H3PO4, right, you're going to do an E2 type elimination, sorry, an E1 type elimination because you're at a secondary carbon. So you're going to make a carbocation and you're going to get a rearrangement. Rings don't rearrange, right? But we can be two possible products, right? We could get where we get a methyl shift. Oh, sorry, too many methyl shifted there. Get a methyl shift, or we could get a hydride shift. So this is from the 1,2-methyl. Or it would be from a 1,2 hydride shift. For you ask, on an exam, I would take either one. This isn't exactly the greatest problem ever. Right? And then this one, you get that product there. So if I have alpha, beta, and beta, those two beta carbons are the same. You're going to get the same product regardless of which way you do your elimination. Let me go back to that one example real quick. Don't lose everyone. All right, so when we had this, treat that with acid. And get that carbocation. You can move a methyl. And get a carbocation here. And then that will do your elimination to give you that. Or I could move this hydrogen. Whoop. Makes that noise too. And you'd have your hydrogen would go here, your positive charge would be on that carbon. And typically it's better to eliminate and have your double bond in a ring than out of a ring. So that would give you that product there. So that's where those come from. So far so good. So we can turn double bonds, we can turn alcohols into halides. We can turn alcohols into tosylate and then do SN2, E2 type chemistry with them. We can turn alcohols into double bonds with either sulfuric acid or with phosphorus oxychloride. So these are all of our alcohol reactions that I kind of classified at the beginning of the group of slides as we go all the way up to the beginning here as nucleophilic reactions, right, where the lone pair is attacking something, right? Oxidation reactions is what we're going to cover next. So oxidations, there's a nucleophilic reaction that happens, and then you get you change the number of carbon-oxygen bonds that are in your molecule. So basically there are 3 types of alcohol, so you get 3 different types of products. So we go back to our thing here. So if we look at oxidations, right, if you're doing oxidations, right, if you have a primary alcohol, right, and again, we're going to use the generic OX for oxidant. You can convert that alcohol into an aldehyde or a carboxylic acid. So this carbon on our alcohol ends up being that carbon there of our aldehyde or that carbon of our carboxylic acid. Don't forget, some people may, that there is a hydrogen on your aldehyde. Right, so I start out with 2 hydrogens on my alcohol here and here. I end up with 1 hydrogen, so 1, 2. I end up with 1 hydrogen here and 0 hydrogens here. So for an oxidation to happen, there has to be a hydrogen on the carbon of your alcohol. So for so you must have a hydrogen on the carbon that your alcohol is on. It looks like I gave this pen to like a 5-year-old. This is terrible. I blame the all-powerful whiteboard. All right. So what that means is now if you have a secondary alcohol, go back for a second. So if you look at going from a primary alcohol to an aldehyde, so if you look at going from primary alcohol to your aldehyde, you remove 1 hydrogen from your red carbon. So 1 hydrogen is removed from that carbon. To go from an alcohol to a carboxylic acid, you have to remove 2 hydrogens. Right? If you don't have 2 hydrogens to remove, you can't oxidize that carbon to a carboxylic acid. So if we look at a secondary alcohol, treat a secondary alcohol with an oxidant, you can only make a ketone. So it's alcohol to ketone. Right? Since there's only 1 hydrogen, there's only 1 hydrogen on that carbon. You can only remove that 1 hydrogen and end up with a ketone. So secondary alcohols always get oxidized to ketones. Tertiary alcohols do not get oxidized. There are no hydrogens on the carbon of your alcohol, right? So on this carbon right here, there are no hydrogens. So there's no hydrogen to remove as you do the oxidation. So you cannot oxidize tertiary alcohols. Right. So the choice of oxidant that you make impacts what product you're going to see in your reaction. So there are oxidants that will convert primary alcohols to aldehydes, and there are other oxidants that will convert primary alcohols to carboxylic acids. So first we're going to look at converting primary alcohols to aldehydes. So there are three reagents we can use to do this. So if you have an alcohol, you treat it with Des Martin per IO. Should I spell this right? Per Denane. There we go. I'm sorry. Right, but since it's a recording, you can just like fast forward over all the rough parts. Right. So can treat with desmartinperidine. This is oftentimes abbreviated, and I will abbreviate on exams as DMP. This will convert your alcohol to an aldehyde. And that is all it will do, is it'll take a primary alcohol and turn it into an aldehyde. Right? You can use Swern conditions. So you do a Swern oxidation. So a Swern oxidation, again, turns your primary alcohol into an aldehyde. Swern will get written as Swern, or it can be written out as all the reagents that make up Swern. Right, so Swern is actually a mixture of reagents. It just kind of gets shorthanded as the dude's name who discovered it. Right, so if you got Swern, so you can either write Swern, or it can be written as Swern, do the oxidation, or the components of Swern. So those components are COCl2. So it's two of this whole, of this piece. So this piece, right, it's two of these COCLs, right? Then you have DMSO. And triethylamine. So again, sometimes it'll just be written as Swern. Other times it'll have these three reagents that make up the Swern reaction. And again, you will convert your alcohol to an aldehyde. And the last one will be PCC. Alcohol to aldehyde. I wish this thing told me how long I was talking. I forgot to start my my timer. I feel like I'm going strong. So, of course, it would not be a complete lecture without a mechanism. And the mechanism we're not going to do the mechanism for all of these, but we're going to do the mechanism for one of them, and that is going to be the Dess-Martin reaction. So probably the hardest part of this mechanism is remembering the structure for Dess-Martin, or for Dess-Martin pyridine. Before you ask, I will not give you the structure. If I ask you the mechanism, you have to remember the structure. Because I'm a bad person. Right, so it's an iodide that has 3 acetates on it, and then is attached to an aromatic ring, and then to another oxygen to make this weird 5-murder ring structure. Right, I'm going to use lots of slides here to get this all in. So we're going to have our alcohol. That alcohol will attack the iodide. The iodide is really electron poor. Will attack the iodide and knock an acetate off of the molecule. That will give us, trying to see the best way to draw this. I don't have tons of board space here. Oops, I get that, plus I get the acetate that I knocked off. Yeah, and it's negatively charged. That acetate can now act as a base and remove the proton from my positively charged oxygen. Pushing electrons back down on the oxygen. I'm going to go to the next slide. That is going to give us that structure right there. Now I'm going to redraw this. I need to draw the acetate, so the OAC. I need to draw this OAC out to do the next step of the reaction and kind of move some stuff around. So I'm going to draw this big. So this is the exact same structure we just had, but I'm just going to draw it larger so you can see all the arrows that are happening in this reaction. Well, I'm going to tell myself I'm drawing it larger. I don't know if I am or not now. All right, so I'm going to draw out the whole acetate. This acetate can just be small and don't care about it. All right, so the acetate is O carbon, O methyl, right? And then we'll have my oxygen, O. I'm going to flip it over a little bit. I need to draw in that hydrogen. Now what I'll do is, there's a bunch of arrows that are going to happen all at once here. These electrons will come out, grab that hydrogen. The electrons in the carbon-hydrogen bond, right? Hydrogen can only make one bond, so it gives its electrons this way towards the oxygen. That oxygen doesn't want to make 3 bonds, so it will give its electrons it'll push the electrons in the bond that it's sharing with iodide over onto the iodide. And then these electrons in this iodide oxygen bond come all the way over here and remake acetate. So I'm going to draw this, see if I can get this all on this slide. No promises. Because I want to have them side by side for you. Oh, we might get there. Right, so if I don't move the oxygen, I end up with, there's my aldehyde. This carbon right here, will make it blue, so it sticks out, is this carbon right here. And then if I just draw it as it kind of is, that's my acetate. Right, so you have, let me get that together. So, there you go. Oh. We'll go green for a second. Right, so this right here, you can see my green. Is this molecule right here, all these carbons. And then oxygen. Yellow, hopefully. I don't know how it's going to show up. Oh, it's kind of awesome. So then this molecule right here is here, and then got all the colors in the world, but apparently I only get 5 of them. And then this hydrogen ends up being the hydrogen that is right there. So that's kind of how everything moves. Everything, all these arrows in this structure, so all the arrows over here, all these are happening at the same time, so they're all moving at once. So Swern, Dess-Martin, and what's it called? Swern, Dess-Martin, and PCC are mild oxidants that will only oxidize your alcohol to an aldehyde. Once it gets to the aldehyde, these reagents stop reacting. Now, you can have stronger oxidants that will oxidize a primary alcohol all the way to a carboxylic acid. Right? So we have sodium dichromate that will do this. We have a chromium oxide and water. And then we have KMNO4. Right? Let's go over here. So if you have an alcohol, oops, stick with my black theme here for my structures. Once you have your alcohol, right, if you have Na2Cr2O7 and sulfuric acid, you will oxidize your alcohol all the way to the carboxylic acid. So you'll remove both protons from that hydrogen. Sorry, you'll move both protons, move both hydrogens from your red dot carbon, and that will give you your carboxylic acid. Now, to do a better job of writing this reagent, Na2Cr2O7, pass this over that arrow if it's a little hard to see. Right? That doesn't actually do anything. Doesn't do the oxidation. What happens is when you mix this with sulfuric acid, you will make so I'll draw this consistently here. Sorry. You'll make 2 molecules of chromic acid. The chromic acid is actually what does the oxidation. The sodium dichromate doesn't do an oxidation at all. Another reagent is, change up my substrate a little bit. Chromium oxide and water, and that will again turn your alcohol into a carboxylic acid. Again, red dot carbon to red dot carbon. Backing up the whiteboard. So again, chromium oxide does not do the oxidation. Chromium oxide reacts with water to give you chromic acid again. So both sodium dichromate and sulfuric acid and chromium oxide and water, they essentially give you the exact same oxidant in the reaction that give you chromic acid. Right. And then lastly, last on our list, but first in our hearts really, is potassium permanganate, KMnO4. This will react with a primary alcohol to give you a carboxylic acid. Yeah. So all of these oxidants, these three go beyond the aldehyde, and they will oxidize the aldehyde into a carboxylic acid. So your primary alcohol becomes a carboxylic acid. Now, hopefully, I've talked for 50 minutes because I forgot to start my timer. So this is where we're going to end. We'll do a brief review of this on Monday. We'll go over some more examples, and then we'll roll into the oxidation of secondary alcohols. And if I had to guess, we might actually make it to ether starting on Monday. There's a chance. So I will see you Monday, and hopefully this will get done, and we'll start on ethers probably on Wednesday. All right. I will sign off by dancing now.